Mankind has always looked to the stars. Since time immemorial, the universe has been a source of fascination and fundamental questions. What else is out there? How was all this created? Where do we come from? When we talk about spaceflight, we think of rockets and astronauts and adventurous journeys to far-off worlds. But real spaceflight takes place very close to us in Earth orbit and unmanned. Well over 1,000 satellites are circling our planet, providing pictures and information faster and with greater precision than ever before. Without satellites, life in our modern world would be inconceivable. Welcome to Spacetime with Ulrich Walter, astronaut and scientist. He knows, in space, incredible things are in store for us. Satellites determine our everyday lives, presenting a view of the Earth from space, guiding data flows through orbiting, providing mankind with information. These are the true achievements of spaceflight. But through ultra-sensitive sensor and camera technology, radar beams and measuring techniques, satellites also provide us with views of the Earth earlier generations could never even have dreamt of.
The last 10 or 20 years have seen great achievements in Earth observation. Take optical telescopes, for instance. Today, they have a resolution of 20 to 25 centimeters. In other words, details of such minute size are visible from space on Earth's surface. We can transmit radar beams to Earth and see the reflected beam not only by day, but also by night. We can even look through clouds. Radar interferometry enables us to determine digital elevation models with an accuracy of 10 centimeters. In the infrared range, we can observe the growth of corn. We can see precisely when a specific variety is ripe. In other words, we have got our world under control. But do we really need that?
Satellites are among mankind's greatest inventions. We don't notice them, but they influence every second of our daily lives. And satellites not only determine everyday life in a modern world, they also keep a watchful eye on our planet. The Earth's surface covers an area of 500 million square kilometers and is subject to constant change. In prehistoric times, it was mainly the cycles of the ice ages which influenced the climate and ecosystems, but today, man is playing a significant part in shaping the environment. These changes, whether they are triggered by nature or by humans, are observed by the eyes in space. It was only the advent of spaceflight that provided us with this precise view of our planet. The monitors in orbit around it provide a digitized picture of the state of Mother Earth.
Earth observation offers direct practical applications. Whether we're talking about agriculture, weather forecasting, or dealing with catastrophes, Earth observation has become something of a new phase of infrastructure in our daily lives.
Ever since the first records from space were kept, data have been stored and compared time and again with the present. Scientists and researchers can thus draw on a vast source of knowledge.
We have the possibility to see changes. In other words, through observing regions regularly, we can identify change processes. We then analyze these processes to determine the causes and assess what can be done with regard to the future.
Autumn 1946, the White Sands U.S. Army test site in the desert of New Mexico. Scientists are preparing to launch a captured German V-2 rocket from the Second World War. But instead of an explosive charge, the V-2 is carrying a 35mm film camera. Hitler's former reprisal weapon provided the first picture of the Earth taken from space. In 1957, the Soviet Union launched the world's first satellite into Earth orbit. Sputnik marked the dawn of a new era. Initially, satellites were put solely to military use. With their spies in space, the Americans looked deep into communist backyards. In a similar way, the Soviets spied on the class enemy in the West. It was the time of the Cold War.
In the 1960s, it was mainly about being able to peer into your neighbor's garden. That's to say, when you're orbiting the Earth, you can look down. And, of course, in one fell swoop, see everything you can't observe from home. And there's no doubt that that was one motivation for putting satellites simply to military or security use. But it quickly became clear that one huge advantage of this technology was that it enabled change processes on Earth to be monitored.
In 1960, the United States launched TIRUS-1, its first weather satellite. The research program consisted of 10 satellites which, on a daily basis, supplied the US Meteorological Service with pictures of cloud formations. It marked the start of modern weather observation. It was only the view of physical and chemical processes in the Earth's atmosphere from space that enabled scientists to record and evaluate global correlations in weather activity.
In recent years, we've been able to make a clear improvement in forecasting quality, even medium range. So in the last 10 to 15 years, forecasting accuracy regarding the next 3 to 5 days, for instance, has become much better. And that is mainly the result of satellite data and their extremely precise monitoring and status description.
Satellites globally collect measurement data from the atmosphere and from the surface of our planet. The data are processed by supercomputers. Algorithms produce models of current weather activity, and it is not just about the weather forecasts for the next day.
I don't always need a weather forecast. 25 degrees Celsius today, 26 tomorrow. That interests no one. But if it's 25 degrees today and a tsunami is going to hit tomorrow because a tsunami forms relatively quickly, the weather forecast is most certainly of interest. And over the next few years, I believe we will see further advances to rule out surprises and give earlier warnings. This will be a core product of good satellites, which will supply us with the data.
The latest generation of weather satellites operates with a previously unknown image quality. The US GOES-16 satellite takes a high-resolution picture of the Western Hemisphere every 15 minutes and one of the United States every 5 minutes. With regard to current events like a hurricane, GOES-16 transmits a picture to Earth every 30 seconds.
Precisely what types of satellites are there? And where are they flying? Let's take a look at Earth. Here we have one kind of satellite, known as a geostationary satellite. Geosatellites are in position 36,000 kilometers above the Earth. That's roughly this distance. Why is that so special? Well, on this orbit, the satellites circle the Earth just as fast as the Earth is rotating on its own axis. So, if I'm somewhere in Europe, I can have my satellite dish always aligned with the same spot, and I always see the satellite at the same spot. This is very important for television satellites. Then, in medium Earth orbit, as it's known, we have the navigation satellites, like GPS satellites and the European Galileo satellites. What's really important, and this is also where most satellites operate, is what we call low Earth orbit. It's the range on this scale of about 1 to 5 centimeters, between roughly 400 and 1,000 kilometers from the Earth's surface. But why so near? Well, Earth observation satellites have to operate very close to the surface of our planet in order to have higher resolution. And here, too, there are various types of satellites, because it makes a difference whether I always fly along the equator, because then that's all I'll see. But if I want to cover the entire surface of the Earth, I have to fly what is known an inclination, an orbit at angles to the equator. Then the satellite flies around the Earth on a north-south orbit. And since the Earth is rotating below the satellite, I see a lot more of its surface. The perfect Earth observation satellites, which most of them are, fly over the poles, because when the Earth rotates beneath them, the entire surface of our planet is visible.
The information obtained from outer space is also of great economic importance. Through the Copernicus program, Europe has created its own observation system, an efficient infrastructure for Earth observation and for geo-information services.
Copernicus has also made Europe largely independent of international observation missions. Today, we already have 5 Sentinel satellites in orbit. That's the name of these satellites, Earth's guardians, so to speak, which scan the Earth's surface round the clock in different resolutions and frequency ranges. The European Union utilizes this information for its own analysis programs and for subordinated political decisions. Whether we are talking about security, agriculture, or climate development, all these data are evaluated regularly to generate information which is also used for political decision-making.
Unité, top, allumage P80 et décollage.
Through the Sentinel satellites, Europe wants to see with its own eyes what condition our planet is in. The Sentinels transmit their data to Earth 24/7. The satellites have their gaze firmly fixed on parameters such as temperature, forest cover, ocean currents, vegetation patterns, urbanization, and the composition of the atmosphere.
What's particularly important with regard to the whole issue of global warming is the measurement of CO2 and other greenhouse gases. And we can also do this with satellites. We can measure their concentration, for instance. Is it increasing or diminishing? Are there regional differences? All this information is used to feed climate models and also to make forecasts as to where our climate is heading.
The Copernicus program links data from space with information from the ground, and in doing so, provides a detailed picture of the Earth. What is more, the Sentinel data are available to anyone free of charge.
We can now monitor systematically and extensively and integrate this information into existing measuring networks even more effectively. As is known, many environmental parameters are well recorded in selective or point measurements, but now a more extensive picture can be obtained with such measurements.
Equipped with high-performance instruments, the Sentinel satellites monitor our planet. Most of the data are used for environmental protection. With information from Copernicus, climate researchers analyze the global changes in our world.
Our Sentinel satellites are on polar orbits, circling the Earth every 90 minutes. So we see the polar ice caps of Greenland and Antarctica every 90 minutes, and any changes in the sea ice. We see how the glaciers are melting and how the huge ice caps in the north and the south are also melting with considerable speed. Naturally, we put this down to climate change.
The Sentinels also record ice loss and gain in the region around the poles. These are important factors for climate models and climate forecasts and for checking their reliability.
There have, of course, also been climate changes in the past without human influence. But there is much evidence, and it is also my firm conviction, that today climate change is being caused mainly by man. Through the satellites, we are able to monitor a good 50% of the most important parameters and show that something is happening.
The satellites continually scan our planet, providing a wealth of data, which will also be accessible in the future. In only a few years' time, there could be technologies which will derive totally new findings from the data.
What is the actual purpose of the European Copernicus program? Well, the ESA has a long tradition. We have been involved in environmental observation for decades, and Copernicus is designed precisely to continue this tradition. In the years ahead, a total of 11 satellites will be launched. The space industry will develop these satellites and put them in orbit. And with regard to the environment, it's not only about rainforest clearance, but about much more. For example, ocean current flow. How does the atmosphere change? And what fume particles and pollution are currently in the atmosphere? Where's ozone formed and where's there too little of it? All this involves the environment. In this respect, the ESA looks back on a long tradition. Although the program costs 6 or 7 billion euros, it's an excellent investment.
Spring 2015, Nepal and the Himalayas were shaken by a series of earthquakes which claimed several thousand lives. Relief teams from all over the world made for the disaster area. The eyes in outer space also focused on it. In next to no time, the satellites provided data and high-resolution pictures.
We were informed via the Geophone Network. The seismic network of the Geo Research Center in Potsdam told us about the earthquake. We immediately began to record the first satellite data, and a team from the Technical Assistance Organization set off for Kathmandu. Parallel to that, we provided analyses. We mapped the damage, showing which buildings had been destroyed and which roads were now impassable. And we didn't just focus on Kathmandu. We also produced evaluations of remote mountain regions where the earthquakes had caused landslides, burying some roads and making them unusable. This was vital information for many relief organizations which had gone to the region.
When disaster strikes, Earth observation satellites can provide information on the regions affected, along with high-resolution pictures. Regional and political borders are irrelevant.
When we talk of climate change, when we think of global disasters or something, international exchange is extremely important. Many years ago, we drew up a Space and Major Disasters Charter. Consequently, when a catastrophe occurs somewhere in the world, an avalanche, an earthquake, a volcanic eruption, or whatever, all the signatories to the Charter are called upon to provide data, and they do so free of charge. That costs money, of course. Nonetheless, they provide relief teams with helpful data free of charge.
To enable relief teams to work more effectively, the Copernicus program also provides data which have been processed already.
Remote sensing can, of course, achieve a great deal. But obviously, this also calls for people with the appropriate training and for an infrastructure which enables the analyses that are now possible to be used operationally.
Satellites have become indispensable helpers for disasters of all kinds. Their images and three-dimensional terrain depictions provide an exact picture of the situation.
It's essential for the relief organizations going to the regions affected to have up-to-date information. How much damage has been caused? Where is the situation worst? What is the scale of the destruction? Where are there open areas? Places where, for example, tents could be put up for storing supplies or providing shelter for people. With our satellites, we can provide all this information from space and help relief organizations with up-to-date maps.
Terrain models produced from space data can show changes on the ground with great accuracy and perhaps help to prevent future catastrophes.
Systematic observation and evaluation and detecting small signs can lead to a more accurate forecast of where on specific slopes greater movement can possibly be expected. So people can be warned The best early warning system is, of course, precise analysis of how big the maximum Mars movement could be and the size of the zone that could be affected.
But it is not only in the case of natural disasters that satellites provide valuable services. The environment is threatened most of all by humans themselves. The effects of human activity are precisely observed and analyzed by the spies in orbit. Water covers 2/3 of the Earth's surface, a vast area that can only be monitored from space.
We can also make appropriate analyses in the case of man-made catastrophes and industrial accidents. Take, for instance, oil pollution resulting from a tanker accident. Once again, we mainly use radar satellites, which are excellent for detecting oil slicks. A film of oil has a smoothing effect. The radar data show this and enable us to make an evaluation, document the current situation, and also observe and document the spread of this oil slick over a longer period.
Satellites monitor the world's oceans in their entirety. Sea quakes are a major threat. They trigger tsunamis, which can cause disastrous flooding. In December 2004, the floor of the Indian Ocean shook. The giant wave this caused claimed over 250,000 lives. As a result of this catastrophe, a worldwide warning system was set up. It utilizes one of the space industry's greatest achievements, the satellite-based navigation system, known for short as GPS. It monitors the position of sensors and buoys. Any change in their position triggers an alarm. The navigation systems in space probably have the biggest influence on life on Earth and have changed it more than anything else.
But how exactly does a satellite navigation system work? Let's take a look at the European Galileo system. A satellite navigation system is based on the Walker constellation, as it's known. What's that? It involves a specific number of orbits. In this case, we see 3 orbits. 1, 2, 3. A total of 30 satellites are located on these 3 orbits. On average, 10 on each. However, only 9 are active. 1 is always a spare satellite. These satellites circle on this orbit an even distance apart. One characteristic of a Walker constellation is that when one satellite is at one spot on its orbit, the other satellite on the other orbit is at a certain distance away. This constellation guarantees that when I'm on the Earth and want to determine my position, I always see at least 4 satellites at the same time. What happens then is that each of these satellites transmits a signal to Earth. My receiver detects these 4 signals and does the following. With the signals from 3 satellites, it determines its position via what we call triangulation. But to do this, it needs the exact time, accurate to a microsecond. And it gets this via the 4th satellite. That's how it all works.
Basically, Galileo, the European navigation system, functions exactly the same way as GPS, but it offers independence. Russia and China have also developed their own systems. Modern devices access the data from all systems. Accuracy has increased enormously.
Since the late 90s, we've been working in Kyrgyzstan. And from our first GPS reading, we didn't know which side of a river we were on. We still had to compare the coordinates with the map we had with us. Those were the early days.
Man has become accustomed to measuring time accurately. Now, through the navigation systems, he can also do the same with regard to his location.
It is only since the introduction of GPS that we've had a uniform spatial reference system. And that's the prerequisite for any kind of global application, because we always have to locate our data with great spatial accuracy. Without GPS, that would be inconceivable.
Today, satellites in space even determine the routes we take on Earth. Computational models and algorithms guide us through the jungle of modern life and through towns and cities that are growing faster and faster. We have made ourselves dependent on a never-ending stream of data and its worldwide network. Mathematics and physics guide us along our roads, and in future, this will also happen autonomously.
We're now talking about time signals which are so small that they are already being changed through the theory of relativity. So the effects of Einstein's theory of relativity also have to be taken into consideration. Our GPS system is a constant test, so to speak, of the theory of relativity. Without Einstein's theory, our GPS system would only function to an accuracy of 1 kilometer. The meter range accuracy we have today is achieved through taking the corrections of the theory of relativity into account. So basically, when driving, each one of us tests Einstein's theory with great accuracy. Wow, we say, it seems to be right.
We have got used to being able to constantly redetermine our position. Often we are not even aware that satellites help us do this. And we also like to forget that at all times we are revealing exactly where we are.
So what level of positional accuracy do we get from a GPS system? Well, GPS has a theoretical resolution of about 1 meter, but that's never attained. The reason is the ionosphere. This layer surrounding the Earth mainly contains free electrons, and these cause minute time differences. Time differences mean distance differences, and thus positional inaccuracies of around 15 meters. So with open standards, which are what we have in a car, for instance, the positional accuracy is no better than 15 meters. But there are tricks. One involves what we call an overlay system, like the EGNOS system. These additional satellites have the correction data, the ionospheric densities, and transmit them to the user. Naturally, this requires a receiver, but then these GPS data can be corrected to obtain a positional precision of approximately 4 meters. With regard to safety, such systems are of great benefit in aviation. And even greater accuracy is possible. Take agriculture, for example. A farmer who plans to sow seed positions his own reference transmitter about 100 meters away. A differential GPS, as we call it. Data from this reference transmitter doesn't have to pass through the ionosphere, but goes straight to the receiver. This results in an accuracy of a few centimeters, usually 1 centimeter to be precise. This enables the tractor to follow a perfectly straight line. Our Galileo system combines both GPS and EGNOS. This means that while an open standard offers an accuracy of no better than 10 to 15 meters, Galileo also transmits highly accurate correction data, guaranteeing a precision in the 1 centimeter range. But such data have to be purchased.
Satellites in Earth orbit have their eyes on coasts, mountain ranges, glaciers and cities. They observe every corner of our planet. Satellites analyze the Earth's atmosphere, monitor the state of the ozone layer, and register every change in climate. The spatially and temporally high-resolution data stream from space offers applications which 20 years ago were not even thought of.
The Sentinel-2 satellite supplies data with a resolution of 10 meters. The instrument has 13 spectral channels, which measure in the optical range and in the close and medium infrared range. This varying spectral information enables us to deduce what is growing somewhere, like different types of cereal and their state of growth. We can tell if there is any water stress and whether fertilizer is required. All this can be seen in the signal we receive from the satellite.
For a world geared to optimal yields, freely available data from space are invaluable. The cameras and sensors of satellites register not only the global distribution of arable land, but also what is growing on it, whether a field is wet or dry, and whether there is a need for fertilizer.
There are companies which take Sentinel-2 data, for instance, for monitoring growth in agriculture. They add GPS data and feed the data into tractors, for example. We call this precision farming. The information tells us where we can farm more effectively, use fertilizer more productively. It tells us where water is needed and where plants are under stress. We can deduce all this from satellite data, and that is the service these companies sell.
Satellites document the condition of the world's forests and the different types of land use. In combination with other data, like those from weather satellites, for example, this information can also be used to forecast future developments.
Vegetation is a key element on planet Earth in many respects. Where there are vast forests, there is also great biodiversity. Forests are also important for the climate system because they bind CO2 on the surface of the land. For their part, agricultural areas are important for food production. Maintaining a balance between economy and ecology is, of course, a major challenge for each individual country and every association of states.
Satellites help us gain a better understanding of processes on our planet. They observe the globe in its entirety. Scientists need the data from space in order to determine the state of the Earth.
We need precise data in order to test the many models we produce. I don't think there is any doubt that climate change is taking place. That's undisputed. Its effects, as we know, are projected in models. And to determine these effects exactly, we need a database. You simply cannot produce good models if you do not have data that are absolutely accurate and reliable.
The Earth is a living structure which is constantly changing. In order to record the topography of our planet exactly, the German Aerospace Center, the DLR, launched its Tandem X mission. In a complicated space ballet, two virtually identical satellites orbit the Earth and scan its surface with radar equipment. This produces a global three-dimensional terrain model of previously unattained precision.
3D models are needed for everything. And before remote sensing was introduced, the 3D models were mapped. They are the origin of all mapping. And remote sensing is practically the successor to classic mapping. Topography, relief, has always interested man more than anything else.
Tandem X surveys the Earth anew, recording all details of its surface down to the size of individual trees.
Through the Tandem X mission, we have created a global elevation model, which is unique in its precision and uniformity. It's unsurpassed by any other elevation model.
The data obtained can be combined with other physical and socio-economic information. Application of these goes far beyond the creation of a topographical map. Soil conditions can be determined. So can the location of bodies of water. The high-resolution data can be used, for instance, to produce maps of potential flood areas and to simulate hydrological drainage models. The two radar satellites can see through areas of rain and identify expanses of water with particular clarity. Water acts like a mirror. Untroubled by cloud cover, the two satellites have scanned our planet day and night to establish a comprehensive terrain data bank of the entire planet. It is the most precise map in the world.
So how does the SAR principle function? Or to put it another way, how can it measure elevation? Let's look at a mountain on Earth. This is the Earth's surface. Here, for example, we have a mountain. And somewhere up here, the satellite is orbiting. Characteristically, it has solar cells on solar panels of the left and right-hand side. So what does the SAR satellite do? It transmits radar waves to various points. For example, to the highest point, the summit, from where the rays are then reflected back to the satellite. Rays are also transmitted to the foot of the mountain, and they too are reflected back to the satellite. What the satellite now does is analyze the time taken for the rays to come back from the summit and the foot of the mountain. The travel time from the summit is far shorter. From this information, the satellite can calculate the height of the mountain indirectly.
The flying eyes in space also monitor the world's seas. Often they are the only way of seeing what is happening in the vastness of the oceans. Marine conservationists use satellite data to pinpoint environmental offenders. Time and again, for cost reasons, tankers flush oil residues into the sea instead of disposing of them in port.
We receive an initial evaluation within half an hour of the satellite pass. In Germany, we have an aircraft ready for every satellite image we've ordered. And if the satellite picture shows something unusual, the pilot is sent out to make a specific check. The advantage of radar satellites is that they can work day and night, and independently. We find our black sheep at night, too.
Shipbuilders and shipping companies can also make use of the signals from space. Rolls-Royce, the British manufacturer of, amongst other things, marine technology, is working on a system which will enable ships to be steered over the oceans from a virtual bridge. The basic prerequisites for this are not only exact positioning determination from space, but also high-resolution images in real time.
Today, pictures of the Earth are available in various resolutions. Here, for example, we have a video from the space station showing individual cities at night. It presents nearly half the globe. The small, bright flashes we see are typical of night in the tropics. You can see them everywhere. We are now flying over the sea, and all we can see are the white of the clouds and the blue of the ocean. This is a typical nighttime view. And here at the top, you can see little green strips, a small albedo, which is also characteristic of nighttime. There are also totally different data, like the Google data you're familiar with. We can zoom in. Here, for example, we have Berlin. We can see details from a resolution of a few meters down to just centimeters. So the resolution is very high. Here we can see individual cars on the road. When we pan down a bit, we see individual buildings and can even look for our own house. These are the typical applications of pictures like these. The drawback is that characteristically these Google images can be a few years old. But that's also the reason why anyone can see them. Then there are these pictures, which are totally different, like those from Digital Globe, for instance, which have to be paid for. The resolutions are even slightly higher. Accuracy is 20 centimeters. They're available every day and can be bought. You can then see whether your boat is still there somewhere in the Mediterranean and whether your neighbor's boat is also there. Those then are all the details and the applications of Earth observation images.
Satellites continuously scan the Earth with the entire light spectrum, observing with radar and lasers, and recording events on our planet in increasingly better resolution. And researchers are coming up with ever better ways of unveiling even the last secrets of our planet.
There's biomass, a satellite which will indeed measure biomass. Then we've got FLEX, which will measure photosynthesis and fluorescence from space. These are all new technologies which are only just being developed. Only 10 years ago, we wouldn't have thought that to be possible.
But today it is even possible to track sandstorms from space. Satellites observe the desert dust from the Sahara on its way around the world and produce exact three-dimensional models. This is just one of countless applications which climate and nature researchers are developing. More and more and increasingly sophisticated data are being obtained and stored.
The most valuable data are those from the past, which I can access time and again in the future. It makes absolutely no difference if the data are only spatially or temporally of very high resolution. A satellite has its own particular strength and specific application.
Continuous observation from space also shows the rapidly increasing urbanization of our planet. Over the last 20 years, the population of Las Vegas, a city in the desert, has more than doubled.
The market for space-based applications like Earth observation, as well as communication and navigation, has grown considerably, especially in recent years. The term new space refers to the increasing number of small firms which are becoming involved and developing their own business areas. For example, with small, extremely compact and easy-to-launch satellites. These technologies are based on the assumption that the data obtained can somehow also be sold to generate revenue.
The new generation of mini-satellites, cube satellites, will play an increasing role in Earth observation. Used as a swarm, they open up totally new observation scenarios. For example, a specific region could be scanned several times a day.
If they could be archived on a daily basis, such data would of course be a big help with tasks like Mars movement monitoring. We could then reconstruct situations retroactively for more remote regions, for instance, and determine when an event occurred. This concentration, which is also possible with regard to temporal resolution, is highly interesting. Small satellites will not be able to achieve everything because, of course, they have their technical limitations, but they can close major gaps, especially where the temporal repetition rate is concerned. And that makes them an interesting complementary development.
Small satellites are used primarily by universities for research programs, but they are also opening up totally new fields of business. The car industry, security and insurance companies have already shown great interest in specialized data from space. And who knows, soon perhaps, individuals will have their own private satellite in orbit.
What would be exciting, of course, would be to have satellite pictures in real time, to view a region with Google Earth and see everything in motion. Being able to scan the Earth in real time would be fantastic. It would have a charm all its own, but we're still away from achieving that.
The Canadian company Earthcast has conducted successful tests with high-resolution real-time videos from space. The resolution from a height of 400 kilometers is so good that individual vehicles can easily be recognized. The special camera is mounted on the International Space Station and focuses on an area roughly 5 by 3 kilometers in size. Earthcast plans to market the pictures, but it also wants to make them available to government organizations. However, the resolution is not yet good enough for identifying people.
There's a difference between spotting and identifying. At the moment, Earth observation techniques do not enable us to identify someone from space and say, you were there at such and such a time. There is this limit of 40 centimeters, and I cannot imagine it being significantly reduced to such an extent that the data could be put to civil use. Higher resolutions most certainly exist in the military sector, but these are put to highly specific and selected use. And they're classified. They're not available to the general public.
Big Brother is watching you from space. The technology and operations of high-resolution spy satellites are kept secret. What is certain, though, is that recording technology offered by private companies is getting ever better.
So what does the future hold for Earth observation? We study so many characteristics of our atmosphere and the oceans that in the future we will be able to hear the Earth cough, so to speak. Furthermore, radar resolution will steadily improve down to the millimeter range and provide us with the most minute details. The question is whether we will even store such vast quantities of data. The same thing also applies to optics, to optical resolution. What can I see precisely? But here, it's unlikely that we will get below 10 centimeters because in the field of optics, we need large telescopes. The bigger the telescope, the better the resolution. So with size being a major factor, the trend would again be towards bigger satellites. And there, we face limits. So in the future, will we be collecting a fine from space? No. And for two reasons. This 10-centimeter resolution is not sufficient for identifying something as small as a number plate. Secondly, number plates are vertical and the satellite looks down from above. So fortunately, it will never be able to read a number plate. In other words, in the future too, you'll be able to drive without worrying.
Only since humankind advanced into space has it been possible to see the beauty of Earth in its entirety. The view from space enables us to understand the global correlations of our planet, and that is just the beginning.
One of the main reasons we engage in research is to come up with surprises. We want to know what's going on and what we can learn from it. And I'm convinced that such surprises will also come in Earth observation. In the future, we'll be able to observe things from space, which we cannot measure today.
Satellites have changed our everyday lives. Indeed, they determine them. Science and research are gaining deeper and deeper insights into the system we call Earth. But it will also be possible to derive totally new commercial applications for data from space.
Remote sensing data will perhaps no longer have the special position they still enjoy today, but will just be one data source amongst many.
We will collect more and more data on our planet more and more quickly. Combining these data from space with information obtained on Earth will lead to totally new discoveries.
It's only through Earth observation satellites that we've come to a comprehensive understanding of our planet. That's because they can observe the Earth in its entirety and thus yield information that would otherwise be unobtainable. Furthermore, every picture that presents our Earth on television shows mankind, time and again, that we live on a relatively small planet with a relatively thin atmosphere, and that we should perhaps be careful not to place too great a burden on our planet through our daily lives.
This stock-taking from space documents the degree to which humankind has appropriated the Earth. It warns us to use our resources sparingly. Thus, the data that are gathered also serve as evidence for future generations, institutions, and politicians.
So what does the future hold with regard to Earth observation? For a start, let's take optical telescopes. I think resolution will move towards the 10-centimeter range, but not far below that. That's because the telescopes would get a lot bigger and exceed all satellite dimensions. Things look a bit different in the radar sector. We can obtain better resolutions without increasing the size of radar telescopes. It's doubtful, though, that we really want that, because every improvement in resolution with a factor of 10 means increasing the volume of data by a factor of 100. What's more, the data have to be stored somewhere, and there must also be someone to look at these data and say, that's exactly what I want. So it's doubtful whether resolution will get better and better. It will, however, be interesting to see what the future really has in store.
Satellites enable us to communicate worldwide. They provide television signals and connect us with the entire globe. The eyes in space also help us to better understand our world. But above all, in future, the flood of information from Earth orbit will reveal how much man is changing his planet.